What's up, everybody? It's A-Dubs in the physics classroom, and today we're going to race two objects to see how their shape and size impacts their final velocity.
Let's go to the first group. Madhav and Craig, what do you have over here?
Okay, we got two hoops. They're the same shape, as you can tell. We're going to race them down this round.
Okay, Craig. Oh! Ladies, what did you see?
So both of them ended at the same time, and so that means the velocity at the end was the same.
Okay.
And to prove that, we set up an energy equation.
So the equation's like, because this is potential energy because it has potential energy, and then because it's rotating, it has like kinetic rotational, and then at the end, because it's like kinetic, it has kinetic translational.
Got
and then
it.
we broke that down in the next step.
And we could use the same equation because since both of the objects are the same shape, they have the same inertia. And then we further broke that down by replacing the inertia with mr squared and replacing the angular velocity with the linear velocity.
Yeah.
And then we canceled out all of the masses and radii.
And we got this after simplifying it, and the final equation doesn't have mass or radius anywhere in it, and so even though both of the objects had the same different masses and radiuses, since it doesn't affect the velocity, they both ended at the same time.
Interesting stuff. Group 3, we've got two different objects over here, right? So now we've got two different objects. What two objects do we have?
We got a solid sphere and a solid disc.
A solid sphere and a solid disc. And what do we expect to happen here? Different shapes and different sizes.
Yeah.
You ready? Don't use the meter stick, Bradley. It never works that way. Okay. Goodness gracious. All right, let's hear it.
You gonna count it down?
Sure. 3, 2, 1.
And which one won?
Solid sphere.
Was it obvious? The solid sphere won. Okay, here we go. Here we go. Get out of the way. They're trying to explain that. Different shapes, Margaret.
First of all. Okay, so first, same equation as they did, which was potential energy is equivalent to the kinetic rotational energy as well as the kinetic linear energy. And so we set up our equation, mgh is equivalent to 1/2 inertia angular velocity squared plus 1/2 mass velocity squared. And you can see here that all the mass cancels out because all the terms in the equation all have mass in them, which leaves us with gh is equivalent to 1/2 inertia without the mass of the disk, and then times the more linearized version of the angular velocity, and then plus 1/2 v squared. And then, as you can see here, r squares all cancel out, so then r is also out of the equation, which means that both the mass and the radius are canceled out. And then that leaves us with gh is equivalent to 1/4 v squared plus 1/2 v squared, gh is equivalent to 3/4 v squared, and finally our v is equivalent to square root of 4/3 gh.
For the sphere, we use the same basic equation, but I equals 2/5 mr squared, so we use that instead. Again, all the masses cancel out, and then when we make omega a linearized v over r, all the r's cancel out too, and then we're left with v equals square root of 10 gh over 7.
And how we know the sphere wins is because 10/7 is greater than 4/3 if we make the denominator the same. So sphere wins.
Oh, interesting. So, if we're thinking about what we've learned today, we raced objects of different sizes and different shapes down a ramp. I hope what we can take away from the experiment we saw and the data or the math on the board is that the only thing that dictates an object's ability to have velocity down the ramp is its shape. Not its mass, not its radius, but its shape. Its distribution of mass, the coefficient in front of its rotational inertia value. As always, if you have questions, drop in the comments. Send me an email or ask me in class. Until next time, see ya!